Hello, my name is James Fodor, and you're listening to the Science of Everything podcast, in which I discuss a wide variety of topics in the natural and social sciences in an attempt to better understand the world in which we live. This is episode number 9, and the topic for today is matter and molecules. So in this episode we're going to look at, matter and the properties of matter. We're going to have a bit of a look at the states of matter, physical and chemical change. We'll examine the nature of atoms versus elements versus molecules and how those are all different. And conclude with a look at some more interesting topics of molecules, for example, chemical formula and macromolecules and the other different types of molecules that exist. Okay, so we'll start off with just looking at matter itself. What is matter? Well, you might know from the famous equation E equals mc squared, where E stands for energy and m stands for matter, that energy and matter are related. So in a sense, matter is a form of congealed energy, in that you can convert a lot of energy into a small amount of matter, or a small amount of matter into a large amount of energy. That's how nuclear power works, by converting a very small amount of matter from uranium into a large amount of energy. So fundamentally, we don't really know what matter is, but one good definition that I came across is that matter is anything that occupies space and has mass. So that obviously includes virtually everything we know of. Trees, houses, planets, stars, dust, people, etc. It doesn't include things like light or fields, and that's about it really. There aren't too many things that don't have any mass. Photons don't have mass. And there may be some other subatomic particles that don't have any. But so apart from a few things like that, pretty much everything that we know of is matter. And all the matter that we interact with in a daily setting is composed of atoms. Now there is matter that is not composed of atoms, mostly very small subatomic particles like neutrinos that we don't really observe. But for our intents and purposes, all matter that really matters to us is composed of atoms. Sometimes these atoms are found by themselves, isolated, but more often they're found bound together in well-defined clusters of atoms that are called molecules. So, molecules are just groups of atoms all bonded together. And how do atoms bond together, you might ask? Well, it works because atoms have electrons, which are electrically charged. And so by exchanging electrons between atoms, they can take advantage of this electrical attraction between the nucleus and the electrons, and so they are sort of glued together in that sense. So it's electromagnetic attraction that keeps molecules bound together, and we'll do a whole episode on that later on, or maybe more than one episode on how atoms and molecules bond together. But for the moment, just remember that it's through electromagnetic interaction, or the same interaction basically that keeps your magnets on the fridge. Okay, so the states of matter. As you may have heard, matter comes in a few different states. There are three main ones that are relevant to us: solids, liquids, and gases. You're probably familiar with those, but what do they actually mean? Well, in solids, the atoms or molecules are packed closely together and do not move relative to each other. So that's not entirely correct, because all atoms are actually in motion, but in solids, the atoms or molecules all they do is vibrate a little bit on the spot. They don't really move from one place to another, and they don't really move relative to each other, so they're kind of stuck in place. There are two different types of solids. Some of them are crystalline solids, and some are amorphous solids. Crystalline solids have a well-ordered, repeating crystal structure, and examples include things like salt and metals. Whereas amorphous solids, the atoms are stuck in position, but there's no long-range order or pattern to those positions. Examples of that include plastic and glass. So you can compare crystalline solids might be like a group of soldiers all marching in formation, whereas amorphous solids would be just more like a crowd of people. Now liquids are very similar to solids in that they're closely packed together, so most liquids are just about as dense as solids. But unlike solids, the atoms are able to slip and slide past each other, and so they can move around to take the shape of whatever container they're in. Gases are completely different from liquids and solids in that the atoms or molecules are separated by wide distances, and they're completely free to move relative to each other. And in fact, you can compress or expand gases so that you move the molecules or atoms closer together or further apart. You can't do that, or not do it much anyway, with solids or liquids. Now, I just want to take a moment here to talk a bit about glass. I mentioned before that glass is an amorphous solid. Now, you may have heard that glass is actually a liquid that runs very, very slowly, and you may have heard a story about panes of glass in old churches that have been there for hundreds of years being slightly thicker at the bottom as the glass has flowed that way over the many centuries of sitting there. That's actually not correct. This is a little bit controversial, but usually chemists would describe glass as an amorphous solid. So it is a solid, but there's no regular pattern to it. The atoms are just all sort of higgledy-piggledy here and there, but they are stuck in place, so they're not moving. The explanation behind the panes of glass in the old churches story is that back in the Middle Ages, people didn't have the ability to make glass perfectly flat and even as we do now. And so it was common that one side of the pane of glass was a bit thicker than the other side. And when they were putting the panes of glass in, common sense would be to put the thicker side down so it was a bit more stable. So that's why you often see that in old churches. However, you can see examples, or at least so I've heard, that there are examples of the reverse, where the thicker side of the pane is actually pointing upwards, which is clear evidence against the glass as a liquid hypothesis. But anyway, if you hear that one, you can put people right. Glass is actually an amorphous solid. Okay, so moving on, I want to have a look at the composition of matter. So we can divide matter into pure substances and mixtures. Pure substances are those that are comprised of only one type of atom or one type of molecule, and include things like elements and compounds. Okay, so elements are comprised of only one type of atom. And the types of atoms that we talk about usually relate to the number of protons in the nucleus. But we'll talk a bit more about that later. But just remember that in an element there is only one type of atom. And all the atoms are pretty much the same. Whereas compounds are comprised of two or more elements bound together in fixed ratios of atoms. So water is an example of a compound. It has 2 hydrogen atoms to every 1 oxygen atom. That is a compound. So you've got two elements, two different types of atoms, but bound together in a fixed set ratio. So either elements or compounds are examples of pure chemical substances. Now mixtures, on the other hand, are not pure chemical substances. They are the result of mechanical blending or mixing of chemical substances, but without any chemical bonding. So the significance of elements and compounds is that they're all chemically bound together. Mixtures are not chemically bound together. They just sort of mixed together, hence the name. Most things that we see and interact with in ordinary life are actually mixtures. Some of them are more obvious than others, like drinks are mixtures, just like you mix a cocktail or whatever, that's a mixture. But actually, even things like animals, plants, metal alloys, computers, cars, these are all actually mixtures because they're not composed of a single element or single compound. They're a mixture of a whole bunch of different things. Water, or at least water with any impurities in it, which is pretty much any water in the real world, and air are all actually mixtures because they don't have definite chemical formulas. Air, by the way, is a mixture of it's about, I think, 70% nitrogen, most of the rest is oxygen, and then there's a little bit of carbon dioxide and other bits and pieces of everything else. So air is a mixture. Now, atoms, elements, molecules, compounds, all those things have two different types of properties that we can talk about: physical properties and chemical properties. Chemical properties are those that become evident only during a chemical reaction. So that the only way we can work out what the chemical property is to change the substance chemical identity. You can't identify a chemical property just by looking at or touching a substance. You actually have to put it into a chemical reaction. So examples of chemical properties include flammability, toxicity, reactivity, etc. Whereas physical properties are any measurable property of the substance that can be determined simply through observation without having to go through a chemical reaction. Now, under the right conditions, say if you vary the temperature, the pressure, or lighting, etc., physical properties can actually change without altering the underlying chemical structure of a substance. So, for example, if you shine a red light on something versus a blue light, the color will change, and so one of its physical properties will actually change, but the chemical properties of the substance, of course, won't change at all. Examples of physical properties include size, mass, so how much of the thing you have, albedo, which is how much light it reflects, color, as I said before, electric charge, a substance can become electrically charged one way or the other without changing its chemical structure, solubility in water, electrical conductivity, and many other things. Now, just before I mentioned chemical reactions, you may have been wondering what that is. Well, just as there are two different types of properties that we can identify with of substances, there are also two different ways we can change a substance, or two different types of things we can do to it. Those are physical changes and chemical changes. Now, physical changes are sort of the more superficial changes. They're changes in physical properties, but not relating to the chemical properties. So physical changes include such things as changes in shape, changes in its temperature, changes in pressure, also changes in state, so like melting and boiling and so on, breaking it into pieces. All of these things are just changes in the physical state. Physical changes don't actually affect the underlying identity or chemical structure of the substance, whereas chemical changes do affect the atomic composition or structure of the substance. So examples of chemical changes include rusting, burning, and acid-base reactions and other such things like that. So the key thing is that chemical changes always involve the transfer of atoms and or molecules and changes in their bonding relationships. Physical changes do not. Well, you might have atoms moving this way or that way, if you break a substance up into multiple pieces, but there's no changing in their relationships at a microscopic level, or electrons or atoms moving from here to there. That's the key difference between a physical change and a chemical change. And finally, one last point before we move on to look at atoms and elements. And this is the concept of the conservation of matter. In chemical reactions, the amount of matter does not change. It always has to be the same before and after the reaction. Now, as I mentioned before, the formula E equals mc squared tells us that we can convert matter into energy, so that's sort of a violation of the conservation of matter, but that's only relevant to nuclear reactions, which is not something that we're looking at in this podcast. We're just looking at chemical reactions. So in ordinary chemical reactions, which are most of the things that we see every day, nuclear reactions are actually quite rare in ordinary life, unless you work in a nuclear power plant or something. In chemical reactions, the number of atoms before and after the reaction must always be exactly the same. The atoms may change position, they may change in bonding relationships, they may change in phase and state, but they cannot change in the types of atoms that are there. So if you have 10 hydrogen atoms that go into a chemical reaction, 10 hydrogen atoms have to come out, even if they come out bonded to different things or in different states or whatever. So that's the important concept of the conservation of matter. That also implies, by the way, the conservation of mass. So whenever you have a chemical reaction, like for example if you burn something, it may seem like some mass has gone away, but actually the mass has just been converted into a different form. So some of the hydrogen within the substance has reacted with oxygen in the air to form carbon dioxide and also water vapor, which then have gone up into the atmosphere and are not visible to you, and you can't weigh them, but they still exist. So you cannot eliminate any mass or matter through chemical reactions. Alright, so now let's move on to the second topic for today and look at atoms, elements, and their differences. Atoms are comprised almost entirely of empty space. A tiny central nucleus containing almost all the mass is surrounded by a sparse cloud of electrons. And this will be familiar from the previous podcast about the history of the atom. Now, you might ask, if atoms are almost completely empty space, why does everything feel so hard? If I hit the table, it doesn't sound like it's empty space. Well, the reason for that is because the empty space is on such a small, tiny scale. If you imagine like a jungle gym full of metal bars all connected to each other, if you're close up to one of those, it looks fairly sparse. Most of it's empty space. But if it was a massive jungle gym and you would stand a long way away, it would look pretty solid. And in fact, if you move two of these jungle gyms up next to each other, they'd clank and they wouldn't move together, even though most of them is empty space. So that's an analogy by which you can understand that just because atoms are mostly empty space, it doesn't really matter, because the empty space occurs at such a small scale that it's not apparent to us as macroscopic objects. Now, the atomic nucleus, which is very, very much smaller than the atom itself, is comprised of protons and neutrons, two different subatomic particles. Both protons and neutrons are about the same size, about the same mass, but the proton is positively charged with a charge of +1, while the neutron is neutral, hence the name. Now, the electrons that orbit around the nucleus are much smaller than the proton. They have only about 1/2000th of its mass, but they have the same magnitude of charge, except they have a negative charge, so a charge of -1. This idea of the electric charge of atoms. The reason that we don't seem to see electric charge in our macroscopic life is because although all atoms are composed of charged particles, most large objects are electrically neutral. The protons and neutrons at a large scale always balance each other out, and so you don't generally see charged objects unless you have a look at a Van de Graaff generator or something similar, which generates a static charge. Electric charge itself is a fundamental property of most subatomic particles. We know that like charges repel, so two positives repel, opposite charges attract. We can use sophisticated equations and various other models to describe this behavior very accurately, but we don't really know at a fundamental level why it occurs. It just does. So you can keep asking why, but eventually you get to the stage where, well, we don't really know, for example, why protons are positively charged and why protons and electrons attract each other. We just know that they do. And if you start asking why about those sorts of questions, you just end up into either metaphysics or theology, really. Although the string theorists are working on that to try and develop a theory of everything, which may perhaps explain why these things work the way they do. But for now, we just have to accept that electric charges exist and they work the way they do. Just another thing I'd like to point out is that this electric charge of electrons is actually what keeps macroscopic objects apart. So, for example, if you touch the table, it feels like you're touching the table or whatever other object you're touching. You can push on it and it seems to push back. But actually, none of the atoms, or probably none of the atoms in your hand or the table, are actually touching each other. It's actually the repulsive forces of the electron clouds in your hand and the table which are pushing each other apart. Nothing's actually touching anything else. And that's actually rather an interesting concept. So when you think of objects being on top of each other or touching each other, chances are no atoms are actually in contact. It's just electrostatic forces repelling each other. Anyway, what is an element? A chemical element is a pure substance comprised of one type of atom, as I mentioned before. Now, we distinguish elements by their atomic number, which refers specifically to the number of protons in the nucleus. Common examples of elements include iron, copper, silver, gold, hydrogen, carbon, oxygen, etc. Now, the reason we classify elements by the number of protons rather than the number of neutrons or the number of electrons is because, well, in the case of electrons can be added and removed from atoms relatively easily. In fact, it happens in most chemical reactions. And you can have a charged atom, which is called an ion, and so computers and all other electronic goods work on that property of moving electrons around. So it just wouldn't work so well to classify things according to the number of electrons they have. As for neutrons, they are not electrically charged, so they're not so relevant to chemical reactions. So it wouldn't be very useful to classify things according to neutrons. And so that's why we use protons, hence an atomic number, to classify the different elements. There are 92 known naturally occurring elements, plus about 20 more that have been artificially created, although most of these artificial ones decay very, very quickly, and so they're not really used for anything. And each element has its own unique atomic number, its own unique name, and chemical symbol. You may have seen these chemical symbols written in chemical equations and so on. Usually the symbols consist of the first one or two letters of the element's English name, like Al for aluminium, or aluminum for my American listeners. But some older elements have symbols based upon their Greek or Latin names. For example, Au is a symbol for gold, and Ag is a symbol for silver, K is a symbol for potassium, and so on. So if you see some funny symbols like that, that's where they come from, old Greek and Latin names. There's a lot of Greek and Latin in science. The planets are all named after old Greek and Roman gods. The words used in biology are all based on, and species names and organ names and so on are all based on old Latin words. The symbols used in mathematics are, many of them derive from the Greek alphabet and Latin letters and so on. So it's very interesting to see what influence that has had. Anyway, now I want to talk about the periodic table, or the periodic table of elements. Now this was devised by a guy named Mendeleev in the late 19th century, and basically it's just a convenient way to classify and organize all the different elements. I'm sure you've seen periodic tables before. It's just a big table with all the elements on it, listed in order of increasing atomic number. So we start with 1 hydrogen and end up with, I think the newest element that's just been discovered is copernicium or copernicium. I'm not sure how it's pronounced. Right at the end, and all the others in between. However, it's not just a list of elements in atomic number, because you'll see that the periodic table is arranged into columns. And each column is arranged such that if you move down the rows, each row of elements share similar properties. So, for example, the rightmost row on the periodic table are called the noble gases, and they're all gases, and they're all inert, so they don't really react with anything very much, and they all have similar properties. So argon, krypton, xenon, gases like that, helium as well, all share similar properties, and so on for the other columns. So that's why it's called the periodic table, because it's periodic. The properties of elements repeat every so often, and so that's how the table is organized, based on those repeating properties. Now, there are many different subclassifications and particular types of elements on the periodic table, but for our purposes, the most important distinction is between metals and non-metals. Most elements are actually metals, and these are found to the left-hand side of the periodic table, and most of the bottom as well. These are all metals. They tend to be good conductors of electricity and heat. They tend to be malleable and ductile. Malleable means that you can hammer them into sheets. Ductile means you can draw them into long strings. They also tend to be shiny and silver in color, and solid at room temperature. Non-metals are those to the top right-hand corner of the periodic table. There aren't too many of them. They tend to be poor conductors and brittle, and generally they're gases at room temperature. Classic examples include oxygen, nitrogen, and things like that. Now, that's a bit of a coverage of how we classify elements according to the number of protons. But I just want to have a look quickly at some other ways we can classify elements or different types of atoms. So, when an atom gains or loses electrons, as often occurs in chemical reactions, as I mentioned before, it stays the same element because it still has the same number of protons, but it now has a net electrical charge, and so it becomes what's called an ion. It's a charged version of an atom. Negatively charged ions are those that gain electrons, and these are called anions. Positively charged ions have lost electrons, and these are called cations. Now, a little mnemonic device I learned back at school was that cations are pussitive. Pussitive as in, a cat. Kind of lame, but it helps me to remember it. So maybe it'll help you. So that's how we can look at, different types of atoms with different numbers of electrons. If we look at neutrons, the same element can also have different numbers of neutrons. But once again, if they have the same number of protons, they still have the same they're still the same element, and they still have mostly the same chemical properties. So neutrons don't really change chemical properties. What they do is make the element heavier or lighter if it has more or less neutrons. These different varieties of the same type of element are called isotopes of that element. You may have heard that word before in reference to things like uranium, isotopes of uranium or something like that, because different isotopes are very relevant to things like nuclear energy, because some isotopes are more stable than others, and hence some are radioactive and others are not. So isotopes have often come up in discussions of radioactivity. The mass number of an atom is the same as the number of protons plus the number of neutrons that it has. And the reason that it's defined like that is because although electrons do contribute mass to the atom, they're so tiny that they're really irrelevant. So the mass of an atom is basically determined by protons and neutrons, and we just kind of ignore the electrons and call the sum of the protons and neutrons the mass number of that atom. So the key point to remember is that the same element can have different numbers of electrons, in which case it becomes an ion, or different numbers of neutrons, in which case it becomes an isotope. Now, just to confuse you even more, there's also a third type of variability. So even when molecules have exactly the same elements of exactly the same isotope and exactly the same number of electrons, they're bonded together in the same amount, so we've got the same molecules here, but sometimes the atoms can be just in slightly different position. You can think of a long chain molecule of carbons or something where you have an oxygen on the second carbon atom compared to the fifth carbon atom or something like that. So it's exactly the same types and numbers of atoms and same isotopes, but just in a slightly different arrangement. That's called a structural isomer. And even more subtle is where we can have exactly the same structural isomer, same isotope and everything, but just oriented a bit differently or bent in a slightly different way, and that's called a spatial isomer. So structural isomers, spatial isomers, they both refer to different arrangements of the same molecule, just, moved around a bit. So yes, we can have ions, isotopes, and isomers all of the same element or same compound in the case of isomers. So just keep in mind all the different ways that atoms and molecules can vary. Finally, I just want to conclude by having a bit of a look at molecules and compounds in a bit more detail. Now, there's one thing that's really cool about compounds, and is that they can have completely different properties to the atoms of which they are comprised. So, for example, sodium is a soft, shiny metal that's highly reactive and very poisonous. You don't want to go consuming too much sodium metal anyway. Chlorine, similarly, is a pale yellow gas that's also highly toxic. So you've got sodium and chlorine in their elemental form, highly toxic, not very nice. Put them together, they form a compound called sodium chloride, which is ordinary table salt. This is the classic example. You see it in all the textbooks, but there are heaps of examples of this where compounds can have completely different properties to the elements that make them up, or the atoms that make them up. Another example is water. Water, as you should know, is comprised of 2 hydrogen atoms and 1 oxygen atom. Now, hydrogen is a very light, flammable, and transparent gas. Oxygen is also a gas. It's transparent, and you can't really taste it or see it in any way, and it's required for anything else to burn. I don't know if you call that flammable or not, but anyway, they're both gases. You put them both together and they form water, which is a liquid or sometimes a solid at common temperatures, and obviously very, very different to either hydrogen or oxygen. Instead, if you take one of those two of those oxygens and combine them with a carbon atom, you form carbon dioxide, which is toxic to humans if it's in too large a concentration. So the key point to this is that the properties, the chemical and physical properties of compounds are determined exclusively really by the structure and arrangement of the atoms of which they are made up, and not really what those atoms are. So although we get all sort of focused on the periodic table of elements and looking at all the different elements and how they all do different things, the elements themselves aren't really that important. Well, they sort of are because they form molecules, but you can have molecules that are quite similar to each other, made of completely different atoms, and vice versa. You can have very, very similar molecules with completely different properties. Compare, for example, carbon monoxide to carbon dioxide. The difference is only 1 oxygen atom, but one of them is extraordinarily toxic, which is carbon monoxide. Even a little bit of it will kill you. Whereas carbon dioxide, well, we breathe it out all the time, and it's too much of it's warming up our planet. So, as Carl Sagan said, the beauty of a living thing is not the atoms that go into it, but the way those atoms are put together. And that applies to anything, not just living things. It's the way the atoms are put together that's really important. And that leads us into the concept of chemical formulas. Chemical formulas basically tell us the way atoms are put together, the specific ratios and numbers of atoms. These are generally represented as the chemical symbols for elements, with little subscripts representing the numbers of those atoms in the compound or the chemical substance. And so, for example, we have H2O, which means 2 hydrogen atoms bonded to 1 oxygen atom. And that's just a very simple chemical formula. If you get into organic chemistry and or look up chemicals, perhaps on your bathroom products, look the names up on Wikipedia or something, you'll be able to see the chemical formulas of some of these things are ridiculously long and complicated. So H2O and CO2 are just some very simple examples of that. But the key thing to realize is that compounds or molecules are always comprised of whole number ratios of atoms, and that those ratios are always fixed. They have to be exactly the same. If you change even one of those atoms, so put in an extra hydrogen or an extra oxygen or whatever, that changes the compound. It's now something different, and it may have completely different properties. So that's why chemical formulas are very important. We need to make sure we're getting it right. Now, a note on the different types of molecules that exist. There are quite a number of different types of molecules. I just want to focus on a few here, some of the most basic ones. Atomic elements exist freely in nature as single atoms. So most metals fit into this category. You can find 1 atom of gold just sitting around in nature. Of course, you wouldn't be able to see it, but you theoretically could. Molecular elements, on the other hand, do not exist as single atoms, but are found as small molecules, generally 2 or sometimes 3 atoms bonded together. So hydrogen and oxygen and nitrogen are classical examples of that. The oxygen and nitrogen in the air are not, they're pure elemental substances, but they're not just 1 oxygen or 1 nitrogen atom just floating around. It's actually 2 oxygens and 2 nitrogens bonded together. The reason they do that is to do with the orbital shells of the electrons and filling those up and so on, and we'll look at that in later episodes. But the point is, you can have pure elements, but they don't have to be just one atom. I mean, they can actually be bonded into molecules. So those are molecular elements. There are also molecular compounds, and those are formed between two or more non-metals, and they form single isolated molecules. Now, molecular compounds are distinguished from ionic compounds, which form between one or more metals and one or more non-metals, and they tend to form large repeating lattices rather than individual molecules. Okay, so let's go over that again, because that's a little bit confusing. Molecular compounds you have form between non-metals, which are the ones to the top right of the periodic table. Ionic compounds form between metals and non-metals. And ionic compounds tend to form big lattices or big structures of repeating units. So maybe, for example, in the case of sodium chloride, you might have a sodium atom, and then a chlorine, and then a sodium, and then a chlorine, and sodium, chlorine, etc., and kind of a big three-dimensional lattice. Whereas molecular compounds formed between the nonmetals just form one molecule, or separate distinct molecules, like one water molecule and then another water molecule. They're not big long lattices or chains, or big structures like the ionic compounds are. So that's why ionic compounds, which are things like metals and rocks and minerals and things like that, they're often brittle, so you can crack them and they tend to shatter. And that's because you've essentially hit a soft point in the lattice, which then sort of shatters, kind of like you shatter a diamond. That's another example of a big compound, a lattice compound. Probably the most interesting type of molecules, though, are macromolecules, which, as the name implies, are very, very big molecules. Now, most molecules that you talk about might be a few atoms or a few dozen atoms or even a few hundred atoms long, but macromolecules can become ridiculously huge. DNA is an example of a macromolecule, and these can be hundreds of millions of atoms in size. This is a single molecule. These are all bound together in one molecule. That's quite impressive. Some other things that are macromolecules, there are some inorganic examples as well, including diamond and graphite, which are essentially just one big molecule of carbon atoms all packed together in a certain way. By far the most important and interesting examples of macromolecules are the so-called biopolymers, the molecules that make up cells. And these are, as you may have heard, carbohydrates, proteins, lipids, and nucleic acids. And these can just form enormous structures, particularly proteins and nucleic acids. They can be millions of atoms in size. And the behavior and properties of macromolecules are, as a result, extremely complicated, and so we need to use some very advanced chemical techniques to try and understand these things. But I think it's very interesting that you can just go from very basic chemical properties of chemistry and extrapolate it up through macromolecules, and then once you get to macromolecules, you start looking at cells, and from cells you look at life forms, and before we know it, we're looking at human beings themselves, all from just starting at a base of simple atoms and molecules all interacting with each other. So you are made of macromolecules. It's quite interesting. Anyway, that's all I have for this podcast. Hopefully you learned something. And if you enjoyed the show, please spread the word by posting a review on iTunes or putting a link to my website, which is scienceofeverything.webs.com. I don't think anyone has visited my website yet, so you could be the first. I have very detailed show notes on there of everything I talk about, and some of the podcasts have links to resources as well. And if you have any comments or suggestions or anything else you want to say, feel free to contact me. My email address is fods12, fods12 @gmail.com. Thanks for listening, and I'll speak to you next time.